Power! Sorry, Rob, but there's not going to be explosions this unit, so you're going to be okay. Power. Power is how fast you're doing work. The fancy word is power is the rate at which work is being done on an object. As you take more physics, Brendan, you'll learn that anytime they're talking about a rate, what they're really saying is you're dividing by time. As an example, acceleration is the rate of change of velocity. It's change in velocity over time. It's VF minus VI over T. Power, what would be a good letter to use for power? Capital P, not to be confused with a lowercase p for momentum. How can you tell that's not momentum? Momentum is a vector and has the vector symbol over it. Power is a scalar. And it's defined as work over time. It's how fast you're doing work. It's what makes you tired. If you walk up a flight of stairs and you sprint up a flight of stairs, you've done the same amount of work because the work would be your mass times g times the height. Why are you more tired if you sprint? You've done the same amount of work faster. Power is what makes you tired. It's the difference between walking up a long hill and sprinting up that long hill. Same amount of work, just one you're doing way faster. I guess I can take this one step further. It's also force times distance over time, because work is force times distance. Units. Well, what do I measure work in? What are the units for work? Joules? Per. What are the units for time? No. What are the units for time? So technically power is a joule per second, but it's so important we've given it a name. Power is measured in what? Yes, it is. Symbol capital W. Named after James Watt, who really wasn't that good a scientist, but was a very good PR guy. I really wish the Watt wasn't named after James Watt. I wish they'd named it after someone else. But, pardon me? J.J. Watt? No. Power is also a scalar. What that's going to mean, again, Kareem, is our equations get much nicer too. Okay? Ready, you Wandy? Not on your phone or anything foolish. Put it away. By the way, if you guys haven't figured out, as a group collectively, y'all pretty much suck at trying to be on your phones. And on that note, because you're on the phone, I even saw the light flash. The whole civilization was going because you were on your phone. Stay off your phone. Did it flash again? I'm trying to limp this bulb till the end of the year, because I also know it's got screen burn. It's holding the image there when I go to the next page. Let me just last till the end of the year. You ready? Let's apply this. An electric motor is used with a pulley and a rope to lift a 650 Newton load. You know what? Is that kilograms, Cam, or is that newtons? You know what? That's the weight, not the mass. And remember, weight is mg. Okay? So lift a 650 Newton load from the road up to a height of 12 meters. The job is done in a time of 11 seconds. What's the power output of the motor? Cam, what does this question want me to find? Power is defined as work over time. This equation is on your formula sheet. You might want to look and find out where it is. Now, work, Cam, we defined last lesson as force times distance over time. Yeah? You might want to underline the word lift. That's really the key word, because lifting tells you, first of all, if you're lifting something, which force are you doing work against, Cam? If you're lifting gravity. Oh! Yes? So I'm going to write this. Hang on. Let's erase that little circle. I'm going to write this equals the force of gravity times, and that's vertical. Did they give me a vertical height? I'll go algebraic first, and then we'll plug in numbers just so that when you're studying later on, you know that's another version of power. When you're lifting something, it's going to be 650 mg times 12 meters divided by 11 seconds. I get 709 watts. Okay? So motors often have a wattage, especially electric motors, attached to them. What if this was a 600 watt motor? It means you can't lift it in 11 seconds. It's impossible. It's going to take longer. And so now you can start to think about, I mean, this is kind of a dumb example, but think about big cranes and the big ones you see on skyscrapers. They know how fast they're capable of lifting certain masses, which allows them to estimate okay, how long it's going to take to get scaffolding up, to get this up, and it's all based on the wattage. You can't go faster than the wattage. You can't get faster than the wattage. And the heavier the item, the slower you're going to have to lift it. Another unit of power is the horsepower. This is the imperial standard unit, the same way feet and inches are the imperial standard units for measurement. 1 horsepower is about 750 watts. You don't need to memorize that. If I ever give you a horsepower question, I'll give you the conversion factor in the question. But the horsepower is what James Watt came up with. Do I go on my James Watt? I did. Okay, I'm going to go on my rant later. So the motor in this example would have a horsepower of, well, 709 watts times, hey, let's do a unit conversion practice. I want watts to cancel, so where do I want it in the second fraction? 750 watts is the same as 1 horsepower. I guess I'm going to go 709 times 1 divided by 750. Divided by 750. This is almost 1 horsepower, not quite. 0.945. Repeating, 0.945, I think the 4.5 repeats horsepower. Not a very big motor. Okay. Next one. A 60-kilogram girl runs up a flight of stairs 3.32 meters high in 2.6 seconds. What's her power output in watts? Well, power is work over time. When you lift something, when you climb stairs, what force are you doing work against? So I think we're going to go mg. Times the height. Over time. Let me pause. Is that okay? I skipped Isabella. I didn't write the force times distance over time. I went straight to saying which force, gravity, mg. So I went straight to this line. I skipped this middle step. Is that okay? Yeah. Isabella, what's the mass of this girl? 60? Is that a mass or a weight? That's a mass. I checked kilograms. G. Why not negative? Scalar. Height. You know what? That's about 1 story. It's almost bang on 1 story. 2.6 seconds. How many watts? $751? Yeah. 751. Power is measured in watt. Power is measured in watt. Watts. That's my dumb joke for this unit, Mason. You like it? Good. If 1 horsepower equals 750 watts, what's her power output in horsepower? Almost exactly 1 horsepower. And I did that on purpose. I kind of cooked the numbers here. No, actually, I didn't. So the 3.32, that's a pretty standard 1-story set of stairs. So if you were 60 kilograms and you ran the set of stairs in 2.6 seconds, which is walking medium fast, that's about 1 horsepower. It's about 750 watts. I'm purely doing that, James, because those of you that are in mechanics know that internal combustion engines are measured in horsepower, and I wanted to give you some kind of a frame of reference for what a horsepower is. In fact, let's talk about the horsepower a bit more. The HP, the horsepower, was originally defined by James Watt. James Watt was a scientist, but not really. What he was an improver. He didn't invent the steam engine. He did dramatically improve the steam engine. And he was a very good marketer. So James Watt was in the Industrial Revolution, steam-powered age, 1830s, 1840s. Brendan, he was going to farmers and trying to sell them on a steam engine, and farmers were like, huh? And so this is why I say he was a brilliant marketer. He invented a unit, the horsepower, because all farmers knew how much work a horse could do in one day. So when he said to them, hey, this steam engine has 5 horsepower, what does a farmer immediately think? This will replace what? 5 horses. It was a brilliant. How brilliant? We still use it. Do you know how much work a horse can do in a day? No! But do we still talk about car engines and horsepower? Yeah! That's good marketing. Because now it's a completely useless unit. I have no idea how much work a horse can do in a day. No idea. Don't care. But that's the horsepower. Come back. Okay? So he was looking for a way to describe the power of his newly invented or improved steam engines in terms that people accustomed to using horses to do their work could understand. This engine has 2 horsepower. Oh, so it can lift the same amount of hay into the hayloft as 2 horses can. Gotcha. I can buy that. You could, as a farmer, figure out very quickly whether it was worth buying. How much food do the horses need? How much do they eat? They need to rest. This can keep going all day. Yeah, you know what? This is expensive, but in the long run, I'll come out ahead. Or, no, you know what? I won't come out ahead. So, example 2. How long would it take a 10 horsepower motor to lift a 500 kilogram safe? You know what? Lift up to a window 30 meters above the ground. Okay, we've got an office building. They're installing a new safe. The safe is too big to go through the doorways and the stairs, so they're going to hoist it through the window, and they do this especially all the time in places like New York. Kareem, what's this question want me to find? Oh. Power is work over time. I want to get that by itself. Where is the time right now? In the bottom of a... Bleh. Wait a minute. How could I get the time to the top? So you're saying power times time equals work. That's the same equation, right? Dividing by time on the right, same as timesing by t on the left. How would I get the t by itself now, Mason?
Divide p.
Yes. So here's our equation. Time is work over power. I guess time is force times distance over power. That's what work is. I underlined the word lift. Kareem, which force? When you lift, which force are we doing work against? So this is going to be mg, and instead of d, how about let's put height to remind ourselves, make sure it's vertical? Over power. Kareem, did they give me the mass? Did they give me, 9.8. Did they give me the height? Did they give me the power? Yes and no. Wrong units. They gave me the power. What's the power of this motor? 10 horsepower. What do I want power to be in? Power is measured in watt? We need to do a conversion. 10 horsepower. Where do I want horsepower in the next fraction if I want it to cancel? It's 700 and, oh, no, sorry. 1 horsepower is 750 watts. You know what? I think I can do that in my head. Isn't it just going to be 10 times 750? So a 10 horsepower motor is a 7,500 watt motor. Is that okay, Derek? Now it's plug and chug. I'm kind of curious. By the way, also, if you needed it faster, this motor is incapable of doing it faster. You need to go to a bigger motor. Mass 300, G 9.8, 300, 500, Mr. Duick. Where'd the 3? Oh, 30. That's where I had the 3 in my brain from. 30 meters divided by 7,500. 500 times 9.8 times 30 divided by 7,500. Is this a fraction? Yeah. I don't think I need brackets in the top because it's all timesing. How many things do I have in the bottom? 1, don't need brackets. 19.6 seconds. Okay. So that's a nice question. I'll even say I like that question, like that question, like that question. Although I don't think I'm going to have you do a whole bunch of horsepower conversions on the test. I'll do 1. The rest, I'm a metric guy. We'll do everything in watts. Well, or, see, 1 watt is not very big. Power can also be measured in kilowatts, 1,000 watts, or megawatts, 1,000,000 watts. Or they've just now started talking about gigawatts. That's a lot of power. How many of you have watched the classic movie from the 80s, Back to the Future? Nerd trivia, it drives me crazy that Doc always says gigawatts of power. It's gigawatts, okay? Anyways, nerd trivia. All right. The power of a light bulb is the, oh, yeah, light bulbs are measured in watts. What's that really telling you? How many joules of energy per second this bulb is going to use. A 40-watt bulb uses 40 joules per second. A 100-watt bulb uses 100 joules per second. That's why it's brighter, because it's creating more light energy. What's the power rating of a bulb that consumes 4,200 joules of electrical energy in 70 seconds? Jaden, what's this question you want me to find? Well, power is work over time. Now, I could go force times distance for work. Wait. What's the units for work? What's work measured in? I think that's the work. They told me. 4,200. Jaden, how much time? How many watts is this bulb? 60? Yeah, it's a 60-watt bulb. Okay. Mr. Dueck? Yeah, Robbie. You said work is force times distance. Yeah. And you said if you're not moving something in the same direction as the force, no work is being done. Well, yeah. So what's moving in a bulb? Electrons. And next year, if you take Physics 12, we'll define electric power with a different equation. But it's electrons. And they are moving in the same wire in the same distance. It works. No pun intended on the work, but it works. I always look to see who's the slowest to figure out that we've just turned a page. Oh, you already had. I'm sorry. You're ahead of me. It's like, okay. Braden, a special version of the power equation. So you ready? If we're moving at a constant speed, power is work over time. Yes, that's how we've defined it. And how have we defined work? What is the equation for work? Good. Force times distance over time. Write that. And then do me a favor. Circle these two. What do I measure distance in? Meters. What do I measure time in? That which I've circled would then be meters per second. What is that which I've circled really if it's meters per second? Speed? Okay, first of all, ready? First of all, are we in scalar land or vector land right now? So speed or velocity? It's a speed and not an acceleration. But here is a special, if you are going at a constant speed, here is another way to calculate power. Where is this one handy? Biking. Suppose you're pedaling your bike and you've calculated that you need a constant force of 32 newtons. And how would you get that? Well, this is really like the Tour de France guys when they're in the wind tunnels. Here's some of the studies and calculations that they're doing. So the wind tunnel is applying a constant 32 Newton force of air resistance, and you're pedaling at 12 meters per second. Give me a second here. Suppose you want to figure out how much power that is, because remember, power is really tiredness. Would the Tour de France guys be interested? By the way, have you seen, so the Tour de France, cycling, lots of doping, yes? Lots of cheating. Have you seen the latest one? Yes. So a French company has a documentary where they have videoed a bunch of cyclists, but in infrared. And there is a strange heat signature in the bottom of their bicycle, right where the pedals are. It's glowing hotter than it should be, almost as though inside there was some kind of a heat source, like a, what's the word I'm looking for? It begins with the letter M. Motor. Oh, yeah. And everyone's denying it up and down, and it's pretty tough to test because it's baked right into the frame. But why would right there be glowing much hotter than the rest of the frame? Well, pedaling creates friction. You guys grease those things down. I don't think there's that much friction. If you were creating that much friction, you had a lousy bike. So a little hashtag nerd trivia there. So meanwhile, how much power? Here, what are they asking me to find? Oh, heck. Marcus? Power. Now, my first thought would be to say work over time. There's my first thought. Marcus, in this question, have they given me time in seconds at all? Have they given me work in joules at all? Now, they have given me a force. See it? Have they given me a distance? In other words, can I go force times distance? Say no. Okay. Oh, that was someone's phone there. So this is the process that my mind goes through. If they say find power, I look work times time, work over time. No, they didn't give me that. This is a job for that special version of power. It's going to be the constant force times the constant speed. 32 newtons times 12 seconds. I did some quick Google searching, and apparently 32 newtons, if you're not going crazy fast, is a reasonable air resistance. Of course, as you go faster, what happens to the air resistance? Bigger, smaller, or stays the same? Bigger, and your velocity gets bigger, which means you need more power. This is why it's so much more tiring to pedal faster. It's a double whammy. Force, air resistance goes up, and speed goes up. I get 32 times 12. 384 watts. That means every second you're using 384 joules of energy. Do that for 60 seconds, you'll be feeling it. Do that for an hour, you'll probably really be feeling it. You'll need to refuel. You need to eat some food, have a snack, get some carbs. So power is work over time. Efficiency. Efficiency means how much bang we get for our buck. In other words, how much of the energy that we're supplying goes into doing work, and how much is just wasted as heat or sound. There is a symbol for efficiency. It's sort of like a lowercase n with a long little tail on the one end. Having said that, I didn't even know that that symbol existed until about 10 years ago. I always just wrote this for efficiency. I'll take either. If you want to impress me with your nerd skills, feel free to use the efficiency symbol. It's a Greek letter. What's the it's less writing, so I'm going to use it. What's the equation? Well, efficiency is power out divided by power in. It's actually the same mathematics as when you write a test. If your test is out of 40 and you get 38, how do you calculate your percentage? 38 out divided by 40 marks in. Okay? Or it can be energy out divided by energy in. Or it can be work out divided by work in. The only thing you have to make sure, Cam, don't put watts on the top and joules in the bottom. Make sure it's either watts over watts or joules over joules. Now, I've given you this, but I don't remember this. Here's how I remember this. We live in the real universe. It's always going to be the smaller number divided by the bigger number. Efficiency is always less than 100%. Now, if you have created something with efficiency more than 100%, or the fancy phrase, if you've created something that gives more than unity, not only will you get a Nobel Prize, in about 10 years, you'll be able to buy Bill Gates. If you can solve the energy crisis, if you can create free energy, even with our current technology, if you give us free energy, there's no world crisis we couldn't now engineer our way out of. Global warming, piece of cake, we can engineer our way out of that. If you got free energy, we'll put one of those in every car. No more fossil fuels. Done. Piece of cake. Food shortage? Oh, if you give us free energy, you know what? We can run lights and we can grow food during the nighttime as well as during the daytime. We can have UV lights. We can double our crop production. Piece of cake. Done. I can't think of a single major issue aside from the political countries going to war. But I can't think of a major world crisis where if you could invent what word I'm looking for here? Uninterrupted energy, unlimited energy, we can solve everything. And if you owned the patent on it, you'd be richer than I would be willing to guarantee you'd be the first trillionaire. Probably fairly quickly. Sadly, I see all your eyes gleaming with hope. There are many rules of physics which show that you can never get 100% efficiency. And in fact, many of those rules have a consequence, and one of those rules is also explaining why it is that you must die. Sorry, but you're going to die. Someday, about 150 years from now, all of your atoms will be in other people, just the same way that all of you right now have some select atoms from Buddha and Muhammad and Shakespeare and any major person in history from more than about 50 years ago. Almost certainly, because you're made up of so many atoms, you have at least one of their atoms, because it all goes back into the great circle of life, Simba, the great circle of life. So that's a long rant, Nevada, to say I always remember efficiency is the smaller number divided by the bigger number. And the reason I say that is in Physics 12, there is a question where next to what you're getting out, the word in appears, and next to what you're putting in, the word out appears, and I always have some kid trying to tell me, oh, this is 148% efficient. It's really not. Oh, if you got 38 out of 40 on a test, how do you calculate your percentage? And then technically you also go times 100%. So, okay. If you want to make it a percentage. Or if they give it to you as a percentage, Cam, you got to divide by 100, turn it back into a decimal before you do the math with it. A typical household light bulb transforms energy at the rate of 60 watts, 60 joules per second. Most of the electrical energy, unfortunately, is transformed into heat instead of light. About 57 watts is heat. Some of you may remember there's even a toy that you could buy as a child called an Easy Bake Oven, which used a light bulb to do the baking. Only about 3 watts are light. An incandescent light bulb is only about 5% efficient. The more heat you move around, the higher your wattage. So a kettle, about 1,500 watts. Do I have that here? No, you know what? That's going to be in Physics 12. Stove, about 4,000 watts. Dryer is about 4,000 watts. Blow dryers they're moving a lot of heat around. They're about 1,200 watts. Light bulb, 60 watts. Okay. The power rating of an electrical appliance is almost always printed somewhere on the appliance. If you want to look, you can. How many more am I doing, Mr. Duke? A couple more. Good. A 255 kilogram mass is being lifted straight up at a constant speed. You know what? That's probably something I would mentally underline. By an electric motor, it takes the motor 4 seconds to lift the mass to a height of 12.5 meters. Okay. A. Boyana, what does A want me to find? Well, work is force times distance. Ooh, are we lifting? You know what? That's going to be then the force, mg, gravity, times h. What's the mass, Boyana? Good. G, 9.8. Why not negative, scalar? H, 12.5. 255 times 9.8 times 12.5. It does 31,237.5 joules of work. I'm going to write down 31,200 joules. I'll go to 3 sig figs. I'll round off, but I'll keep that number on my calculator. Beep. Boyana, what's B want me to find? Power. Well, that's work over time. Now, I know how much work, 31,200 and whatever it was. Time. So I'm going to use the full answer, 31237.5, 31237.5 divided by 4 seconds. How about 7,810? If I go to 3 sig figs? Watts of power. That's how many watts, James, we're getting out. Boyana, according to this question, how many watts are we putting in? Part C, what does it say? 12 kilowatts is how many normal watts? 12,000, right? Don't overcome. Kilo is 1,000, so 12,000. We're putting in 12,000 watts. We're getting out 7,810 watts. What does it want me to find? Okay, so efficiency is power out divided by power in. You know what? Smaller number divided by bigger number. 7,810 divided by 12,000, and then I'll go times 100 to change it to a percentage. Boyana, I have this number on my calculator. I'll use my answer button. So if you use the 7,810, will be slightly different. This is about 65% efficient. Oh, times 100. Most of you can probably go from a decimal to a percent in your head without actually timesing by 100, and if you can, great. 65% efficient. Where did the other 45% of the energy go to? Heat, sound, really mostly heat. Heat's the big one. Heat's the big one. Is that all right? Okay. By the way, do your bodies give off a lot of heat? Yeah? Do you think your bodies are terribly efficient? Nope. If you add up the amount of food that you eat, if your body stored all of that to 100% efficiency, wow, you'd all be pretty big. Or you'd all be running around like crazy. You'd all be really fat, or you'd be sprinting around nonstop. But your body burns a lot of it just to keep everything going. Heat. Also, blood pumping up and down. Hey, that's force times distance. That burns some energy as well. Heart muscles, that's a force times the distance. So your body burns a lot of energy just sitting there. Yes?
If you were able to pull something out, would it increase the efficiency?
Do I have any runners here? Anybody run regularly? Or jog? No one does? Do I have soccer players here? Okay, soccer players. What's easier to play in when it's 35 degrees on a hot sunny day, or just when it's winter when it's about 8 degrees on a cold crisp day? What's easier to play soccer in? You can run for a lot longer when it's 8 degrees out. Why? You're spending far less energy cooling your body. Now, that's the external. Internally, the problem is most of the chemical reactions that go on inside you require that very specific temperature. So that's why when your internal gets cold, then the chemical reactions aren't working properly. We have a name for that. It ends in thermia. Okay, that's hypothermia. That's why you get sluggish, your brain's you're not thinking clearly. So that's not efficiency. But certainly, I know when I go running, for example, I can run way better on a cool day than I can on a hot day. Further and faster. And feel better afterwards. Last one. Putting it all together. Hey, and I think next class we might even have a lab finally. I haven't done one for a while. Get to do it. You're going to calculate your own horsepower. Oh, yes. Okay. A girl pushes a, you know what? This is 300 newtons. I think that is mg. It's a weight, not a mass, right? Along the floor for a distance of 4 meters, the coefficient of kinetic friction is 0.33. She then lifts the box straight up 1.22 meters. Okay. What's the minimum amount of work she has done? Now, why did I say minimum amount of work? Let's assume she's pushing it at a constant speed. That's the minimum you can do. In other words, Derek, we're not speeding the box up. Okay with that? I think this question has 2 parts. She does work while sliding the box because there is a force and there is a distance in the same direction. And then she does work in lifting the box. 2 parts. I'm going to divide the page sort of in half, except I know that the lifting is going to take less room, so divide your page kind of like that. And you can call it sliding and lifting. In fact, the lifting part is so easy. Let's do the work for lifting. How about W with a little L, and I'll do W with a little S for sliding in my high-tech system. Because lifting, isn't it always just gravity times the height? Brett, how big is mg in this question? It's so easy that it's tough. So I don't think Brett wrote that down, did he? Right? I don't have to times it by 9.8. Whatever the mass is already multiplied by 9.8, and the answer is 300. If you want the mass, divide by 9.8. We can, but 300. What's the height that she lifted it? That's not the height that she lifted it. Read very carefully, please.
1.2.
Yes? So the lifting part, Brett, how much work did she do? 300 times 1.2. 360 joules? Yes? Okay. What about the sliding? Well, for sliding, work is going to be the force times the distance that she slid it. Now, Brett, the distance that she slid it is pretty easy. What's the distance that she slid it? It is pretty easy. How far did she slide it? 4. Okay, with me so far?
Yeah.
How hard was she pushing it? The question doesn't say. Any thoughts on how we could figure it out? Yeah, impress me.
300 times 0.53. Like 300 times 0.53.
Why? Walk me through your reasoning first.
I don't know how that's if it's a constant force.
Okay, if it's a constant speed,
Speed, sorry, then it should be the same amount of friction acting against it.
if we drew a quick free body diagram, because her work is the applied force. The question is, how big is her applied force? Well, we would have gravity down. Are we sinking into the ground like quicksand? Are we flying into like Superman? Here is her applied force, which I don't know. I don't. But, Sam, if she's at a constant speed, how big is friction compared to the applied force? Ah. Okay? So the reasoning that you guys saw, I'm impressed, is I can go friction times the distance. The directions are opposites, but it'll still give me the same answer. You okay with that, Hayden? And then I heard Brendan say, hey, Mr. Dewick, friction is mu times the normal force, and then times distance. I don't know the normal force. Oh, but look. I know another force the same size as the normal force, mg. Brett, how big is mg exactly as a number? Ah, did you hear him say 300 times mu? So he did about 5 steps all at once. I'm impressed. Derek, you should be impressed. So he said it's going to be 0.33 times 300 times, Brett, what was the distance that we were pushing it? How many joules of work does she do sliding it across the floor? Should be close to 400, 396. That's how much to slide it. That's how much to lift it up. How much work did she do in total? Now here's the nice thing. Although one work is this direction and the other work in lifting is this direction, Cam works a scalar. I can just add them up. I don't need to do anything winner minus loser or anything fancy like that. Just going to be add them up. Cam, in your head, well, on a calculator. No, I'm picking on Brett. How much work did she do grand total? Add them up. Use a calculator if you need to.
756.
Sorry?
756.
756 units for work. Thank you. Did you know that, or you were clever enough to at least look next to here and say that it must be joules because it's true? Okay. All right. Brett, what does B want me to find? Efficiency is smaller number divided by the bigger number. Just make sure your units match. Make sure it's either joules over joules or watts over watts. Don't go watts over joules. Any thoughts on which two numbers I would divide here, my friend? And your hint is, look at part B. Look at what they gave you in part B. What did they give you in part B? In part B? I don't see newtons in part B anywhere. Brett. Right?
Yeah.
And I think that's how much she put in.
Yeah.
How much work did she actually do? So can you tell me what it's going to be? I think it's going to be 756 divided by 1200. Yeah?
163.
Can you make that a percentage for me? Where did the other 37% go? Probably heat. She worked up a sweat. Some of the energy that she burned went into heating up her body and was evaporated as the sweat rolled away. Okay? So we can do an awful lot with this. Last one, stair climbers. Stair climbers. On a stair climber at the gym, a 58-kilogram person lifts their center of mass up 18 centimeters with each step. 18 what? Wait till the end of this. I'm almost done. 18 what?
7 meters.
Nice try. 0.18 meters. You're not going to get me. Right? We have to do math with meters, physics with meters. If they take 500 steps in 10 minutes and their muscles are 20% efficient, then find. Rob, what does part A want me to find?
The rate force the person will put.
What's that really asking me to find?
How much completed?
Nope.
Work.
Psst. 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 Power is the rate at which work is being done.
Power.
Oh, what?
Power.
I just, in this time, decided to give you the actual English definition. Wants me to find power. And power as an equation, Robbie, is what?
Watts times time. No, watts over time, sorry.
Work over time. I know we're running out of English letters because the W by itself is a unit, but here in the equation it's work. You know, on a stair climber, aren't you lifting? So you know what? I think we can go like this. mgh over time. Here we go. Robbie, what's the mass?
58 kilograms.
What's G?
1.8.
What's the height? Careful, it's not 0.18. Can you read to me the second sentence?
500 steps.
If, starting with the word if.
If they take 500 steps.
Okay. I think the height is 500. That's the height. Is that okay, Eugene? I mean, this is how a stair climber works. And the reason I have to do that is time. Robbie, how much time?
10 minutes.
I can't use minutes.
600 seconds.
So I'm going to write up here T equals 10 minutes. How do I go from minutes to seconds? Times by 60. 10 times 60 is it 600 seconds? Now, the other thing I could have done, Eugene, is I could have figured out, well, if they do 500 steps in 10 minutes, I could have figured out how many seconds to do one step. And then I would have used a height of 0.18. But to me, it was easier to say, well, why don't I find the total height, total time? How many watts of power? Also, by the way, this explains why it's possible to burn calories on a stair climber and why a stair climber is better than a treadmill. On a treadmill, really, you're not doing much work. You're actually doing work with the friction of the treadmill, not much more than that. Here, you're doing it against gravity. Do y'all get 85.26? I'll go 85.3. Power's measured in watt? Watts. You gonna make it, James? Last one. B. What does B want me to find?
The rate at which the person moves through it.
You know what? This wants me to find the power he put in. Power out, we got 85.3 watts. It wants, okay, how much power did he put in? Well, it seems to me I can do this. Efficiency is what you get out divided by what you get in, what you put in. This is, if any of you have worked on a treadmill or a stair climber or an elliptical, if you ever have a calorie counter, this is how they calculate it. What do we want to get by itself, Robbie? Where is it right now? Oh, are you saying I can times it right to there? And I'll get efficiency times power in equals power out? Right, Cam? Cam, how would I get the efficiency by itself? He's sweating. He's trying to figure out where the heck I am right now. He's looked away from his phone. He's wondering, what was the symbol? You weren't on your phone? Oh, okay. Cam, do you know what this acronym stands for? Too much information? Okay. Robbie, I'll come back to you. How would I get the efficiency by, or no, how would I get the power in by itself? Divide by what? Yep. Here it is. This is what your stair climbers do. They calculate how much power you put in. And this is also why they ask you for your mass and things quite often. You have to program that in. And then they know the approximate efficiency of an average human. This is also, by the way, why those stair climbers and the calorie count, very inaccurate. Very inaccurate. Because they're using an average optimized efficiency. But if you're a freakish athlete, your body might be way more efficient than someone who's way overweight and out of shape. But how many joules of energy in theory did you burn? So I'm going to go 85. How many watts did you burn? 85.26. And it says we are 0.2% efficient. In theory, 426.3 watts. So this is what we can do with power. It's been we've been doing lots of concepts. Next class, there's going to be a lab. It won't take you all class. I also, the lesson after that, got lots of cool videos, some of my coolest ones. I have some good ones. But for now, my angels is questions you can try. Number 1. Number 2. James, okay, hustle back. Number 2. Please notice that's hours. You'll have to do a conversion. Three is tricky. I won't say 3 is nasty. It's fair game, but barely, and it would be fair game as the nasty multiple choice question on the test. Okay? 4 is good. Skipping 5. 6 is good. 7 is good. And then for mixed questions, number 1, number 2. Three and 4 are the same question. I'll skip 3, 4. 5. 7. I skipped 6. 8. 9. I'm giving you lots, but you're going to get time to work on this next class as well. 9, 10, 11 or 12. 12, elevator. That's a lot. But that's really giving you every way to mix and mash these. The answers are there. Next class, lab activity, and you will have time to finish this. So really, we have a bit of a weird schedule this week. I see you Wednesday. Do I see you next week on Monday? It's a curriculum development day that wasn't there at the beginning of the year, but just got put in a couple of months ago. So really, this assignment is due a week from Wednesday. But you're also going to get a lab tomorrow. It's not like you can just totally work on it in class. Okay?